Have you ever wondered how do you listen to music on the radio? While going through the course, we realized we can design a simple AM radio receiver, but unfortunately Sweden stopped transmitting AM frequencies since 2010, so we decided to design a demodulator and use the oscilloscope to test it. So what is a modulation and demodulation? First, imagine a simple wave. This is called a carrier wave. It's steady, repeating signal that doesn't carry information on its own. Now here's your voice, or any message you want to send. It's messy, complex, and not constant frequency. Radios can only pick up constant frequencies. So what do? We modulate the carrier wave. That means we change something about the wave, either amplitude, frequency, or phase, to embed information. In our case, we performed amplitude modulation, aka AM. That changes the height of the carrier wave to fill in the message wave. The message wave we are sending is mirrored, and then the carrier wave is used to fill it in. This enables us to transmit messages in constant frequencies we can tune our radio to. For testing purposes and accounting for what the oscilloscope allowed, we generated a sample beat that oscillates between 1, 2, and 4 kHz and modulated the wave with a 90 kHz carrier wave using this Python script. We expect to hear a change in tempo since the oscilloscope does not support high enough frequencies to hear a change in tone. As shown by the trace, we expect one long tone corresponding to 1 kHz, two shorter ones corresponding to 2, and 4 even shorter that correspond to the 4 kHz frequency. The receiver takes the modulated wave and now must recover the message from it. This is done by the circuit we designed, a filter and a × 2 operational amplifier to be able to have enough voltage to use a buzzer. In AM modulation, we use a simple but clever circuit. First, a diode clips off the negative half of the modulated wave. This is called half-wave rectification. What's left is a pulsating signal that still follows the shape of the carrier wave. Next, we smooth it out using RC low-pass filter, a resistor and a capacitor in parallel. The capacitor charges and discharges slowly, following the envelope of the wave, while filtering out high-frequency carrier to recover the message wave. But how exactly do we choose the right RC values? We want the RC time constant to do two things: be long enough to smooth out the fast ripples of the carrier wave, and be short enough to follow the slower changes in the message signal. And here is the rule of thumb that helps us choose the RC values. And analyzing our data, we concluded to a 100 kilo ohm resistor and 1 nanofarad capacitor. The result? A clean version of the original message signal. Here we can see the live circuit on the breadboard and the trace as expected. On the breadboard, we can see here the op-amp buffer circuit from lab 2 and 3 that basically removes any rigging from our input. And then we have the IC where we convert +5 to -5 to use in the operational amplifier. Here is the demodulator. We can see the diode and the capacitor connected in parallel in order to create the demodulated wave, and the buzzer where we can hear the sound. The result is a clean version of the original message signal that outlines the carrier wave as seen on the trace here on screen. We can see the red signal following the outline of the modulated blue wave. This is the amplifier circuit used to amplify the wave in order to hear the buzzer. And here we can see the blue wave that is amplification of the red wave in order to be able to use a buzzer and hear the sound of our demodulated wave. And for the result, we apply the waveform and we can hear the change of beat. The first long one, the two consecutive ones at 2 kHz, and then the one at 4 kHz.